Hello everyone, welcome to another video where we'll be discussing questions from JEST, quantum mechanics, and we'll slowly go from basic to advanced questions in this video. So, first question being, these are JEST questions. Okay, so your first question will be, this is the first chapter of quantum mechanics, that is operators, or you can say mathematical tools in quantum mechanics. Okay, so first question, we'll go from basic. Okay. So, consider the following two kits, following two kits. Through the numericals, I will try to explain you the concepts of kit psi is given as, it's a column vector minus I 3 I 2 plus I 4, and kit phi is 2 minus I 2 minus 3. So this is a vector. So a vector is represented as the inner product of bra vector and ket vector. Okay, bra and ket, they mix up to give me bracket, right? So it's written like this. This is a bra vector, and the ket vector is written in the other way. Bra vector is the column is a row vector, like it will be row matrix. You can say matrix, row matrix, and ket vector will be your column matrix. You can see here ket matrix, ket vector is given, ket psi, that is given in the form of column matrix. And the first question is, and yeah, both are complex conjugate of each other. Like bra vector will be the complex conjugate of ket vector. Complex conjugate, if you understand, 2 plus I, it's a complex number. Its conjugate is 2 minus I, like this. Okay. So, and also ket vector is the complex conjugate of bra vector. So, yeah. So this is given ket psi, ket phi. So you have to find what? First question is, you have to find the bra vector of phi. Sorry, it will be written like this. Evaluate the scalar product phi psi. And third question is, examine why the products ket psi and ket phi and ket psi and ket phi, um, and bra phi and bra psi do not make sense. Okay. Examine why the products ket psi, ket phi, and bra psi do not make sense. Okay, so this is the question. Consider the following two kits. So you are given two kits here, right? And you have to find the bra vectors. First question is you have to find bra phi, right? Let's try. As I've told you, bra means your complex conjugate of ket. Okay, so you use this and try to do this question. Okay, so Bra phi will be ket phi complex conjugate. Okay, ket phi was what? 2 minus I, 2 minus 3I. So that will be 2, and it will be the opposite. It will be a column, a row vector. The कह yes, sir. 2 I, 2 plus 3I. 2I, 2 plus 3I, because I is the complex conjugate of minus I. 2 plus 3I is the complication of 2 plus 3I. That's 2 minus 3I, and this is a row vector. Your bra is a row vector. Okay. So this is the first question. Evaluate the scalar product of phi psi. So now phi into ket psi. This is how much? 2I, 2 plus 3I into ket psi is how much? Minus 3I, 2 plus I, 4. Minus 3I, 2 plus I, 4. Okay. So if you see, we'll multiply 2 into minus 3 is minus 6I, okay, plus I into 2 plus I plus, because see, this is your 3 by 1 matrix. This is a 1 by 3. Okay, I made a mistake. Here, 3 columns and 1 row. Okay, my bad again. This is 1 by 3. This is 3 by 1. Okay, one row and 3 columns. My bad. Sorry, 1 row, 3 columns. Here, 3 rows, 1 column. Okay, so these two should be equal. They are. So the resultant matrix will be this one by one. Okay, 1 cross 1 matrix. So this would be, I was doing the right thing actually, but minus 6I plus I whole into 2 plus I plus 2 plus 3I whole into 4. Is it all right? Okay. So minus 6I plus 2I minus 1 plus 8 plus 12I. So if we solve this, minus 4I, 8I plus 7. Okay. So answer is 7 plus 8I. This is the value of phi, inner product of phi and psi. Okay. The final question in this number 1 is, examine why the products get psi, get phi, and this do not make sense. Okay, why they don't make sense? See, first of all, sci-fi, sci-fi. This is these are two Kate vectors. So, see, if you see two Kate vectors, like they will be like this, right? Column vectors. Suppose anything 1, 2, 3, 3, 4, 1. How can we multiply them? Because this is your what? This is your 3 is to 1. This is your 3 is to 1. So these two are not even equal. See, how can two matrices be multiplied? If these two are equal, then the dimension of the other matrix will be this. But here, these two are not equal. So they cannot be multiplied with each other. And we cannot take the inner product this much. So this doesn't make any sense. We will not get the answer of this. Okay. Okay. Exactly here, brass and Wi-Fi also. Both are what? Row vectors. So two row vectors cannot be multiplied like this. Okay, so there is no multiplication, so they don't make sense. Okay, that's the reason. This is how we perceive these things. Okay, mathematically. You can write if you want to write like from linear algebra, from linear algebra, the product of two column matrices, cannot be performed. Okay, and two column matrices or even two row matrices cannot be performed. Okay, yeah, that will be the answer. I hope you understood. Okay. Next is, suppose there is a this psi 1, psi 1 and ket psi 2. When we will say that these two are orthogonal? When we will say these two are orthogonal? When this, the inner product of psi 1 and psi 2 is 0, then we will say what? Psi 1 and psi 2 are orthogonal to each other. Okay. Is it all right? Yeah. Okay. Write a question. Question number 2. Consider two states. Consider two states. Psi 1 is equal to 2i phi 1 plus phi 2 minus a phi 3 plus 4 phi 4. Okay. Psi 2 ket psi 2 is equal to 3 phi 1 minus I phi 2 plus 5 phi 3 minus phi 4. Okay. Where phi 1, phi 2, phi 3 and phi 4 are orthonormal kets. Orthonormal kets. And where a is constant. Where a is a constant. Find the value of a, so that find the value of a, so that psi 1 and psi 2 are orthogonal. Psi 1 and psi 2 are orthogonal. Is it all right? Okay, so psi 1 is given, psi 2 is given. So you have to find it. Psi 1 given, psi 2 given. Yeah. So orthogonal, as I have told you, psi 1 and psi 2 are orthogonal. That means we have to do this psi 1 into psi 2. Okay. But here kate vectors are given, so we have to find the bra vector of it. So bra psi 1 is equal to, just take the complex conjugate of everything, minus 2i. Okay, sorry. Um, okay, for it, okay, minus 2i. Okay, I will write it here so that I can see it from here. Minus 2i phi 1 plus phi 2. Sorry again. Ah, okay, minus a phi 3 plus 4 phi 4, because these are real numbers, so we will not take the minus here. Okay, psi 2 is as usual like that, 3 phi 1 minus I phi 2 plus 5 phi 3 minus phi 4. So for these two to be orthogonal, we will take this inner product should be 0, right? So let's multiply them. So these two will be multiplied and these two will be 1, right? These two will be 1. So minus 2i into 3 plus 1 into minus I, my plus minus a into 5 plus 4 into minus 1 is equal to 0, right? So minus 6i minus I minus 5a minus 4 is equal to 0, minus 7i minus 5a minus 4 is equal to 0. So we have to find a. It's very simple. Just take everything to that side. Minus 5a is equal to 7i plus 4. So a is equal to how much? A is equal to minus 1 by 5, 7i by 4. Okay, is that all right? That is the answer. Mm. Yeah. Okay. Okay, let me write some operators that will be useful. Examples of some operators. So unity operator, unity operator. Okay, first of all, what is an operator? What is an operator? Right on. An operator A is a mathematical tool, mathematical mathematical rule that when applied when applied to a kit sign transforms transforms it into another into another kit another kit psi dash of the same space of the same space, and when it acts when it acts on a bra phi, it transforms it into a into another into another bra phi dash. Is it all right? Okay. Just a transformation of matrices. A psi will be just psi dash. Okay. It will just transform, and A phi, sorry, A phi will be phi dash. Okay. So that's the work of an operator. Hmm. Okay, so let's write some examples of some operators. For example, first operator is called unity operator. Unity. What is a unity operator? Okay, it leaves any kate unchanged. That means, for example, this is a unity operator is acting on psi vector, so it will give psi only. There will be no change in the value or whatever the psi is. It won't change. Okay, and then is gradient operator. Gradient operator. So gradient operator is what? Del psi r. Suppose del psi r will be what? If we write it, del psi r by del r I cap. You know it, right? Oh, sorry, del x. First is del x plus del psi r by del y j cap plus del psi r by del z k cap. Okay? Yeah. So this is a gradient operator. Next is a linear momentum operator. You just remember these things. Linear momentum operator. Linear momentum operator. P psi r is equal to minus ih cut del psi r. Okay, is it all right? This is a momentum operator minus ih cut del. Okay, so it will be applied everywhere. Now Laplacian operator, Laplacian Laplacian operator. What is Laplacian operator? Del square is the Laplacian operator. Del square psi r is equal to del square psi r by del x square, and this is a scalar. Okay, this is not vector. Plus del square psi r divided by del y square plus del square psi r divided by del z square. Is it all right? Okay. Now finally is the parity operator. Final one is the parity operator. Parity operator does what? This is like this parity operator. Psi r is equal to, it changes the parity of the inner part like r. Okay. Say psi minus r. Is it all right? Okay. Now see, uh, just let's product of operators, products of operators. See, the product of two operators, the product of two operators is generally not commutative. Okay, it's not commutative generally. Not commutative means like A into B, that won't be equal to B dot B to A. Okay, and product of operators is associative. The product of operators is associative. Okay, associative means what? For example, there are three operators A, B, C. So I can write it as A will act upon BC is equal to AB can act like on C. Okay, yeah, is it all right? Okay, okay. Let's see. Expectation value of an operator. Expectation value of an operator. Expectation value of an operator. Suppose how will I write it? Expectation value is like this. The sign is like this. So psi A psi divided by inner product of psi and psi. If this is normalized, then psi will become 1, right? But anyway, we have to do it. Hmm. Okay. Next, write down next point. The quantity k to phi into bra psi. Okay, that is product of a k with a bra is a linear operator. Is a linear operator in Dirac's notation. In Dirac's notation. Okay. To see this, we can write it here like this: phi, so psi dash is equal to psi dash into phi. Yeah. Okay. Is it all right? Yeah. Where this thing is actually a complex number. Okay. Yeah. Next give a heading Hermitian adjoint. It's a very important one. Question comes from here in JEST also, and in say subnet Hermitian adjoint. Hermitian adjoint. What is Hermitian adjoint? Hmm? I don't know. The Hermitian adjoint. The Hermitian adjoint or conjugate of a conjugate alpha dagger. This is called dagger. Okay, of a complex number alpha. Of a complex number alpha is the is what actually the complex conjugate of this number. Conjugate. The complex conjugate of this number. Okay. So alpha dagger is equal to what? Alpha star. Hmm. We can write the relation here psi a dagger phi is equal to phi a dagger psi star. Okay. Yeah. So let's write some of the rules of it. Hmm. So some rules. A dagger, whole dagger will be A. Okay. A into A operator whole dagger is equal to A complex conjugate. Sorry, A complex A conjugate into A dagger. A to the power n dagger is equal to A dagger to the power n. Hmm. Operators summation of the operators A plus B plus C plus D whole dagger is equal to, you can take them individually, A dagger plus B dagger plus C dagger plus D dagger. Is it alright? But now the thing is, if I multiply all of them and take their dagger, A, B, C, D whole dagger is equal to D dagger, C dagger. It will be like ulta, okay? This the opposite order. Japanese, no? Japanese, no? Okay. So if I how to do this? If I apply it like this, ବସିଲେ କଲ୍ କରିବ ହେଲା psi D dagger, C dagger, B dagger, A dagger. Okay, yeah. These are some of the rules that you need to remember. Okay. What are Hermitian and anti-Hermitian operators? Hermitian and anti or skew Hermitian. Okay. Skew Hermitian. Skew Hermitian operators. See, uh, an operator A, it's said to be Hermitian. It's said to be Hermitian if it is equal to, if it is equal to its adjoint, if it is equal to its adjoint A dagger. Okay. So A is equal to A dagger, or you can say psi A psi is equal to phi is equal to phi A psi. Okay, you can write like this also. When it is called skew emission, for example, there is another operator B. So B operator is said to be, it's said to be skew or anti-Hermitian, skew or anti-Hermitian, skew or anti-Hermitian if B dagger is equal to minus B, okay, or psi B phi is equal to minus of phi B psi star. Okay. Yeah. Is it all right? Okay. Let's write a question related to it. Question number it will be, I think, three. I think, yeah, three. Question number three. 3A. Discuss the hermeticity of the operator. Hermeticity of the operator A cap plus A cap dagger I. These three operators I will give you, and I. We have to discuss the hermeticity, whether they are Hermitian or not. That's the question. Whether they are Hermitian or not. Find the Hermitian adjoint. Find the Hermitian adjoint of F A cap, which is equal to how much? F A cap, function of A cap is equal to 1 plus I A cap plus 3 A cap square 1 into 1 minus 2 I A cap minus 9 A cap square, okay, square, divided by 5 plus 7 A cap. Alright, last question here in this section, so that through one question we'll be having a lot of concepts clear, so that the expectation value of a Hermitian operator of a Hermitian operator is real and that of an anti-Hermitian operator, that of an anti-Hermitian operator that of an anti-Hermitian operator is imaginary. Okay, so that the expectation value of a Hermitian operator is real and that of an anti-Hermitian operator is imaginary. Please try to solve these three questions. You have 5 minutes. I hope you will take 5 minutes to solve these questions. Okay, please try. I hope we could solve it. Discuss the homogeneity of the operator A plus A dagger. Okay, so how to solve it? Let's see. Okay, suppose it is B operator is equal to A dagger, sorry, A cap plus A cap dagger. So hermeticity, that means I will take the complex conjugate of it, A cap plus A cap dagger, dagger. That will give me what? A dagger plus A dagger and O dagger. So this is actually basically your this one, and I can write it also like this. So this is your Hermitian, isn't it? Because B is equal to B dagger, right? We proved that B is equal to B dagger, so B is Hermitian. Okay. Okay. What is the next operator in this section? What is the next operator? This is Hermitian. Okay. I A plus A dagger. Okay. Let's see. For example, C is equal to I A plus A dagger. Okay. C dagger will be how much? I A plus A dagger whole dagger. So I dagger is minus I, okay, because complex conjugate, and this is A dagger plus A dagger dagger is A, right? So this is what exactly minus C, isn't it? So this is what C is equal to C dagger is equal to minus C, or so this means what C is what skew Hermitian, okay, isn't it? If there is a minus sign, this is what skew Hermitian. Do you agree with me? Do you agree with me? Skew Hermitian or anti Hermitian? Okay, what is the final one? Okay, what is the final one? I A minus A dagger. Okay, let's see this one. For example, there is another operator D. I A cap minus A. So D dagger will be how much? I A minus A dagger whole. So that will be minus I A dagger minus A dagger dagger will be A. So if I multiply the minus inside, it will be I A minus A dagger, isn't it? So if you see, this is actually the original one. So D is equal to D dagger. So this is also omission. So D is omission. I hope you understood. D is omission. Okay. Yeah. What is the next one? What is the next question in option B? Like question B. Find the omission adjoint of f of a, where f of a is this much. Omission adjoint. Omission adjoint. So find the Hermitian adjoint. We have to find the Hermitian adjoint. I mean, simply dagger we have to find, right? This is just a name. So let's write f of a first. F of a is how much? 1 plus I a cap plus 3 a cap square. 1 minus 2 I a cap minus 9 a cap square all divided by 5 plus 7 a cap. This is alright. So f a dagger we have to find. Hmm. So yeah, let's take the whole dagger. Let's first multiply them. 1 minus 2 I a cap minus 9 a cap square plus I a cap minus minus plus plus 2 a cap square. This is minus 9I a cap cube, isn't it? Hmm. And otherwise, you can do one thing actually here. Taking the dagger actually, hmm, if you take the dagger of it, it will actually become what? This one complex conjugate, it will be coming here. This one complex conjugate, it will go there. So 1 plus 2i a cap, a cap dagger, dagger of it, okay, minus 9 a cap dagger square. Just the a cap became a dagger and interchange of positions. Now this one will become what? 1 minus I a dagger. Why minus? Because I conjugate is minus, and plus 3 a dagger square. Okay, okay, divided by 5 plus 7 a dagger. Is it clear? Just the interchange of positions as I have discussed in the definition of it. Okay, yeah. Okay, what is the next option? C. Question number C in this section. So that the expectation value of a Hermitian operator is real and that of an anti-Hermitian operator is imaginary. We have to solve it. So first of all, expectation value of a Hermitian operator is real. Let's see. For example, Hermitian A is a Hermitian operator. That means A is equal to A dagger. So expectation value of A is how much? Psi A psi. Okay. Psi A psi, which can also be written as psi A psi star. Isn't it? Okay. So if A is equal to A dagger here, then what does it mean? It means A is real, isn't it? Of course, A is real. If A is equal to A dagger and this is equal to this star, then A is real. Okay. And for example, for example, for an anti-Hermitian operator, what has happened? For an anti-Hermitian, for an anti-Hermitian operator, B dagger becomes how much? Minus B, isn't it? So again, if I take this one, this will be minus this, isn't it? So this will happen only when B is purely imaginary. Okay, this will happen when this thing is purely imaginary. Okay, so which means that your this or this is purely imaginary, which is the proof. It's a basic logic and understanding. You have to understand it a bit, solve it. Okay, yeah. Okay, next is a projection operator. Next is a projection operator. So I an operator P said to be a projection operator if it is Hermitian and equal to its own square. Okay, if it is Hermitian and equal to its own square, so if I will write it is Hermitian. That means P dagger is equal to P and equal to its own square. That means P square is equal to P. Is it all right? Okay. So the unit operator I can be an example of what? It's a simple example of projection operator. How? If you see I dagger is equal to I and I square is equal to also I. How? If you see simply what is I in matrices. Suppose this is a 3 by 3 matrix. So it's 1 0 0 0 1 0 0 0 1. This is a unit operator, right? Suppose in matrix 3 by 3 matrix. So I dagger will be I, isn't it? If I take the complex conjugate of it, it will be this one only. And I square. If I take the square of it, and it will also be 1 0 0. You can check it yourself. I square will be 1 0 0 0 1 0 0 0 1 into 1 0 0 0 1 0 0 0 1. Let's check it. 1 1 0 0. If you multiply it, you will get 1 0 0 0 1 0 0 0 1. Okay, you can check it yourself. So I square is also I, and I dagger is also I. So I can be a example of what? Projection operator. I hope you are clear about it. Okay. Yeah. So next, write the properties of projection operator. Properties of projection operator. Okay. So the product of two commuting projection operators P1 cap and P2 cap is also a projection operator, because P1 P2 cap is equal to, sorry, dagger is equal to P2 dagger P1 dagger, which is equal to P2 P1, because projection operator means it is Hermitian. So P2 dagger is equal to P2 P2, P1 dagger is equal to P1, and their square will be what? If you see the square, it will be P1 P2. We will just write like this. Okay, square means like multiplied twice. So this is your P1 square P2 square, which is actually again projection operator means square is equal to its original value. Okay, so see, product of two commuting projection operators P1 P2 is also a projection operator. See, is it clear? Yeah. Again, next point is next property. The sum of two projection operators. The sum of two projection operators is generally not a projection operator. Is generally not a projection operator. Okay. Last, no, third point. Two projection operators. Two projection operators are said to be orthogonal. Are said to be orthogonal if their product is zero. If their product is zero. Okay. Yeah. Yeah. Okay. I had a question for it. I had a question. Question number 4, I think it would be. So that the operator, so that the operator psi, get psi, bra psi is a projection operator only when psi is normalized. Try this question. So that the operator psi is a projection operator only when psi is normalized. So that the operator psi is a projection operator only when psi is normalized. Please try this question. See, first of all, see psi dagger is equal to how much? Psi. Okay, because it's Hermitian. If we assume this is Hermitian, okay. For example, you take the square of it, that would be how much? Psi. It's very confusing to write this thing sometimes. Psi. Psi. If you write it this way, this will be. I will open just the brackets. That will be psi. This will be written like this. And if you see, this is what? This is a normalized. If it is normalized only, it will be projection operator. Because if it is normalized, this one will become 1, right? This one will become 1. If it is when it is 1, only when psi is normalized. Only when psi is normalized. If psi is normalized, this will become 1. If it becomes 1, what will be the value? The middle part will vanish. That means psi. And if you see, this is exactly like this. So that means if I write it as p, this is p square. This is your p. So p square is equal to p. And your p Hermitian is already is equal to p. So that means what? P is a projection operator. Is it clear? Yeah? Yeah. I hope you are clear about it. Okay, let's write some properties of commutator algebra. I'll just start it a bit, and next session we'll be discussing that. I'll just start it a bit. Commutator algebra. So the commutation of commutator to operators A B is how much? It's written as A B minus B A. If you know this, an anti-commutator is written in the curly bracket. Anti-commutator is A B plus B A. Okay, this is called what? Anti-commutator. Is it all right? So two operators are said to be commuting when their commutation is 0. Okay? If it is 0, then we will say what? A and B are commuting. Okay. Is it all right? Hmm. Okay. So if it is Hermitian, then what? So not Hermitian. Their dagger will be what? Like this. B dagger, A dagger. And if it is Hermitian, B is Hermitian, then B dagger is equal to B, A is Hermitian, A dagger is. Okay. Okay. Next is commutation of x cap px cap is equal to I h cut I cap is a unit operator. Y cap py cap is equal to I h cut I cap. Hmm. Z cap pz cap is equal to I h cut I cap. Okay. Okay. Properties of commutators. What are the properties? Properties. If AB is equal to minus of BN, this is called antisymmetric. Okay, this is called a property of antisymmetry. Okay, Hermitian conjugate of an operator of a commutator. Hermitian conjugate of a commutator. A B whole dagger is equal to B dagger A dagger. Next property is distributivity. Distributive property. Distributive property is ABC is equal to AB. This will come out first, and then plus this will come out next. Okay, like this. You remember. And the one that is on the which side, it will be on the same side. If C is to the right of B, so it will go out as the right of the commutator. B is to the left of C, so B will come out as a to the left of the commutator. Okay, remember that way. Is it all right? For example, AB is a very important property. A is to the left of B, so it will come out as left and BC operator commutator. And now B is to the right of A, so B will go out as right of the commutator. Okay, it will go this way, this will go this way. Okay, yeah. Next property is Jacobi identity. Jacobi identity. Commutator A, B, C. Is equal to 0. Okay, yeah. Okay. Yeah. So write a homework from these properties. You will try to solve this question. Question number 5, I think it will be. 5 is so that the commutator of two Hermitian operators is anti-Hermitian. Evaluate the commutator. Evaluate the commutator A, B, C. Okay. So these two are your homework. Please try these questions. Okay, and we will continue our session in the next class. Okay. Thanks for watching. Thank you very much for watching. Thank you.